All right, welcome to the introduction to section 4.2. So today we're going to define what's called the definite integral, learn some properties of it, and then learn how we can use limits and right-hand sums as we just looked at to evaluate a definite integral. So here it is. I've shaded here the area between a function f of x and the x-axis on AB. And whatever that area is given this name. This is that area. It's represented as this symbol in words is the definite integral from a to b of f of x. So f of x is the function, dx x is the variable we're working in, and a and b are what are called our limits of integration. Okay, we'll look at a specific example in a few minutes, but this basically says find the area between f of x and the x-axis on the interval from a to b. Okay, let's think about a few properties of this that we can analyze without knowing much more about it, except that it represents an area. So first, the integral from a to b of f of x. How does it relate to the integral from b to a? Well, it's defined to be the opposite. When we switch the limits of integration, these things are defined to be opposites. So it equals the opposite of the integral from a to b of f of x. The integral from a to a, well, if I just came here and I looked just at this, I would have no area to pick up because I have no width on the x-axis. So if I have no area to pick up because I have no width on the x-axis, the value of that integral would be 0. Okay, the integral from a to b of k times f of x, where k is just some number. So that says take your function, shift it up by a factor of k. How is that going to change the area? If I shift up by k, the height here everywhere is going to change by k, and so our area will also change by a factor of k. As with derivatives, areas work similarly. If we take the integral from a to b of f plus g or f minus g, we can do that separately as the integral from a to b of f plus or minus the integral from a to b of g. So those things are equal. And finally, if we have one function that's greater than the other, so here I've drawn a function f. If I had another function here, g, which was smaller than f, then it would seem that the area under a, shaded in red, would be smaller than the area under g, which is shaded in green. So we would get that the integral, the definite integral from a to b of f of x with respect to x is greater than or equal to the integral from a to b. Strictly greater if we know we have the picture above, but if we don't know exactly whether g is greater, could be equal everywhere, we still get that inequality. Okay. So how are we going to evaluate these things? Well, first with some brute force algebra, and then we'll eventually get to a point where we're a little bit quicker and more efficient at doing this. That's where we have to get to. Okay, so here's a definition. If the limit of any Riemann sums, so those sums we were looking at before are RL midpoint sums, those are Riemann sums. We're just going to focus on the right-hand sum. We just need one to be able to do this, and the right-hand sum seems to be the easiest one to get our hands on. If it exists, if the limit as n tends to infinity of Rn exists, then that number is the value of our integral. More generally, if the limit as n goes to infinity of some Riemann sum, so here, this looks like this piece is area of a rectangle. This is, here we are adding the areas. Then we let n get really large. If that limit exists, then it is the value of our integral. In this definition, it says for some c in each interval on the axis, each subinterval, we're going to focus on that right-hand endpoint x sub I and use that for our Riemann sums. Okay, so let's go back. So we had looked at the area between x squared and the x-axis from 0 to 3. So we were looking at that integral. And using this definition above, this integral would equal the limit as n tends to infinity of Rn, which we decided was 27 over n cubed times 1 squared plus 2 squared plus 3 squared. Okay, That is the limit, as n tends to infinity, of 27 over n cubed times, here we have a sum. Our index, it starts at 1, it's the thing that's being squared. It ends at n, and it looks like every time you step the index up, you square it. Okay, I know the value of that sum, not magically, but by experience. I'm not going to justify it for you. I will tell you what this sum is. This sum equals n times n plus 1 times 2n plus 1. I don't think the justifications are in the textbook. I think they're slightly beyond our course. They're maybe for an analysis course. I could be wrong though. I haven't looked recently. But we're going to use these sums. So this sum from I equals 1 to n of I squared looks like this. N times n plus 1 times 2n plus 1 over 6. And you may say, how does that help? Well, it allows us to rewrite this limit without the Riemann sum, without the summation notation, and all in terms of n. So this looks like 27 over n cubed times n plus 1 times 2n plus 1 all over 6. Okay, that looks messy, but it's actually not so bad. This is something that we can handle. Clearly, we know what the denominator is. It's just 6n cubed. Now, let's think about the numerator. When we multiply n times 2n, we're going to get an n cubed. And that's going to be the highest power of n that we're going to get. Let's see, we're going to get an n times 2n. So that's going to be a 2n cubed. So this is going to look like 27 times 2n cubed. Let's see, can we figure out the n squared term? Let's see, we're going to get n times 1 is going to give us an n squared. And then a 2n, let's see, we get n squared plus n. So we're going to get 3n squared, I believe. It actually doesn't matter, plus some other terms. I actually don't care what those terms are. And you may say, well, that seems sloppy. And I would say, well, what do I have here? I know I have a polynomial in the numerator and I have a polynomial in the denominator. And those have the same degree. Those are both third degree polynomials. So this is the limit as n tends to infinity of, I get 27 times 2, 54n cubed plus 27 times 3, 81n squared plus something, all divided by 6n cubed. I actually don't care what that something is because we learned way back in chapter 1 how to handle limits like this when we have the limit of a ratio of polynomials that have the same degree. That limit is the ratio of the leading coefficients, which is 54, 6, or 9. So what did we just show? We just showed that the definite integral from 0 to 3 of x squared dx is equal to 9. And what does that look like in a picture? This is 3, this is 9. We just found that this area is 9 units squared. Okay, so there's a bit of a process there. Here's what we're going to need to do. We got to go get our hands on Rn in general. So what did we do? I used this I waved my magic math wand to tell you what the value of that sum was. But then once I knew the value of that sum, I was able to use our past knowledge about limits to go ahead and find this area. Okay, so if we can generalize this idea of Rn, we can simplify this process a little bit. So I've drawn a picture for you again. Here's some function f. We're looking on the integral from the interval from a to b. So delta x is going to be b minus a over n. And I want to find the area of the rectangles on these intervals that I've drawn in for Rn. Well, all the rectangles have width delta x, and so that's not so bad. I know that part. Now I need the height. So if I look at this first rectangle, the height of this rectangle is the output of the function at x1, which is the y coordinate of this point, or f of x1. So on this interval, the area of my rectangle is just f of x1, which is its height, times delta x, which is its width. Doesn't change much here on this second interval. The height of my rectangle is the output of the function at x2, which is the y coordinate of that point, which is f of x2. 2 times delta x. Similarly, we can keep playing this game. Output of that function is f of x 3 times delta x. Okay, well now I can actually write down Rn then. Rn looks like f of x1 times delta x plus f of x2 times delta x plus, we're going to keep playing this game until we get to this last interval, which is f of xn times delta x. Okay, that's not so bad. I can even write it as a sum. It looks like the sum, we're indexing 1, 2, all the way up to n, so I equals 1 to n of f of x sub I times delta x. Okay, now the question is, can we simplify that f of x sub I? Delta x, we know it's just b minus a over n, whatever those are. Can we simplify that f of x sub I? And it turns out we can. What is x0? x0 is a. What is x1? Well, to get from a to x1 up here, what do? We add delta x. It's a plus delta x. To get from x1 to x2, what do? We add delta x. So x2 is a plus delta x. That's x1 plus another delta x. So it's a plus 2 delta x's. To get to x3, what do? We add a third delta x. We started at a, we went 1, 2, 3 delta x's. A plus 3 delta x's. We'll keep going till we get to xn, which is a plus n delta x's. Okay, so Rn then is the sum from I equals 1 to n of f of a plus, let's see, here's 0, here's a 1, here's a 2, here's a 3. It's just I times delta x. Okay. So there's our n. We're going to put that into practice here in just a second. All right, let's put this into practice with one example. We'll make these notes plenty long, and then you guys can try to head to the activity and see what you can do. Okay, so we want to evaluate the integral from 0 to 2 of x squared plus x delta, or dx. All right, so we got some things we need to get our hands on. The first thing we need to know is, what is delta x? Well, it's b minus a, whoops. It's b minus a divided by n. It's 2 over n. Let's see, let's come back up here. Anywhere in here, x sub I decided was a plus I times delta x. X sub 2, we had moved over 2 delta x's. X sub 3, we had moved over 3 delta x's. So x sub I is a, which is 0, plus I times delta x, which is 2 over n, which is just 2I over n. I really hope my Apple Pencil makes it to the end of this. All right, so then, let's see, we saw Rn. It is the sum from I equals 1 to n of f of xi, which is a plus delta x. So that's 0 plus I times delta x was f of 2I over n times delta x, which was 2 over n. Okay, so a was 0, I is I, it's our index, delta x is 2 over n, so there's a plus I delta x going into the function, multiplying by delta x. All right, now our job is to battle through some algebra. Once we write down Rn, we're going to need to take a limit, but let's try to simplify Rn first, and then we can take that limit after we battle through some algebra. So this is the sum from I equals 1 to n. This is everywhere in my function that I see an x, replace it with a 2I over n. So I get 2I over n squared plus 2I over n. And that is all being multiplied by 2 over n. Okay, so this is the sum from I equals 1 to n of, let's see, what do we get here? We get 4i squared over n. When we multiply that by 2 over n, we get 8i squared over n squared. Plus, we multiply 2 over n by 2i over n, we get 4i over n. Okay, that's not so bad. We can break this up. It doesn't matter if we add these term by term or we add all of the 8i squareds and then all of the 4i over n's. So we can break this up into two sums. It's the sum from I equals 1 to n of 8i squared over n squared plus the sum from I equals 1 to n of 4i over n. Okay, and now the nice thing is when we think about these sums, what's changing? Just the I, right? N is some number. Eventually I'm going to let it get really large, but just the I is changing. So I can actually factor out of these sums every term that doesn't have an I in it. So this first sum looks like 8 over n squared times the sum from I equals 1 to n of I squared, plus the second term looks like 4 over n times the sum from I equals 1 to n of I. Okay. Both of these sums are up here. I didn't state them before, but here are the three sums that we're going to need to know. Well, this one we can justify really easily, just thinking about adding up the first n numbers. Pair them off, 1 and n, 2 and n minus 1, and you'll see what happens. Okay, so we need these first two, and then we should be able to handle this. So this equals 8 over n squared times, okay, this was n times n plus 1 times 2n plus 1 all over 6 plus 4 over n times n plus 1 all over 2. Oops. Sorry, there's some bad arithmetic up here. Let's fix it so we don't have to do this over. Let's do this multiplication again. 4i squared over n squared times 2 over n. This should be an n cubed. 2i over n times 2 over n. I multiply these two things, I should have an n squared. So n cubed, n squared, n cubed, n squared, n cubed, n squared. Sorry about that. Slight multiplication error, but that's going to help our cause tremendously. Okay, so what's happening here? This first term, just like I know where I'm going, I'm going to have to take a limit. So Rn, I get 6n cubed there. I get 2n cubed in the numerator. N times 2n. That's 2n cubed. Multiply that by 8 is 16n cubed plus some other terms. This one I'll write down exactly because it's easy to multiply out. I get 2n squared. And what do I get? I get 4n squared plus 4n. So this is our n, and that tells me then that the integral from 0 to 2 of x squared plus x dx, it is the limit as n tends to infinity of Rn. So that is the limit as n tends to infinity. Well, I can break that limit up at the plus sign. We saw that a long time ago also. So it's 16n cubed plus some other terms over 6n cubed plus the limit as n tends to infinity of 4n squared plus 4n all over 2n squared. And we're in the same situation as we were above. These limits are both the ratios of the leading coefficients, and we get 16 over 6 plus 4 over 2, which looks like 2 plus 2 2/3. So 4 2/3 square units. Okay, when you're doing this and you're looking at a continuous function like this one, which is the only things we're going to look at, how did I find my mistake here in this multiplication is a good question. I realized when I got down here at this line that I wasn't going to have the same degree in the numerator and the denominator. I noticed that. I said, uh-oh, something must have gone wrong. Where was that? And luckily I was quickly able to notice that I made some multiplication errors up here. We could fix those quickly. So expect that that will happen when you get to this final step. Expect that you'll get to the point where you have the same power in the numerator and denominator. Otherwise, an algebra error must have occurred. So there's one to learn from since I made it right here. Okay, that takes some time, some patience, and some algebra. I promise it'll get more efficient eventually, but it's good to see how these ideas developed when they developed as calculus. So see if you can take that and work on the class activity.